We begin with a wavelength of 1 meter. This is our base input. From here, we calculate the frequency by dividing the speed of light by the wavelength. This gives a frequency of 299,792,458 Hz. Next, we calculate the energy using Planck's relation. Multiplying frequency by Planck's constant gives us an energy of approximately 1.986 times 10 to the minus 25th joules. We then divide that energy by the speed of light to find the momentum. The result is numerically equal to Planck's constant. This tells us that at a 1 meter wavelength, the photon's momentum equals h. Now we calculate the equivalent mass by dividing energy by the speed of light squared. The result is approximately 2.2102191 times 10 to the minus 42nd kilograms. This mass value becomes a repeating constant in the system. The time it takes light to travel 1 meter is calculated next. Dividing the wavelength by the speed of light gives a time of approximately 3.3356495 nanoseconds. This value becomes our base time tick and links space and time directly. We then reverse the thermal energy equation to retrieve Boltzmann's constant. Using the energy value and assigning a corresponding temperature, dividing energy by temperature yields a value close to K, confirming consistency across thermodynamic scaling. Now we observe that dividing Planck's constant, in SI units, speed of light, by the speed of light also gives the same constant as the earlier derived mass. That is 666607015 divided by 299792458 equals 2.210210909, which matches the mass value from earlier. This is the scaling constant that ties together energy, mass, frequency, and momentum. To scale further, we now use the wave period, around 3.335 nanoseconds, as the next wavelength input. Repeating this step, we drop into a deeper energy tier. Each tier increases mass, energy, and momentum by a factor of the speed of light. At frequency values near the speed of light squared, a dimensional shift occurs. This system doesn't require any adjustable parameters. The constants emerge naturally from the relationships between wavelength, frequency, energy, and time. Starting from 1 meter, we derive Planck's constant, uncover the thermal scale, and reveal the scaling behavior of dimensional transitions. This is a map of physical structure built entirely from wave relationships.
Okay, now let's see, go back to 1 meter here. And if we take, this is the temperature of the 1 meter wavelength right here. 1 meter frequency, there's the joules. So if we take the temperature now and we use the temperature as wavelength, this is where we see Boltzmann's constant. So this is the superimposed wavelength that's in 1 meter that represents Boltzmann's constant, and all these other measurements or numbers, so these are all superimposed wavelengths right here, like this one right here. This one right here is another constant number. It's Planck's constant. This is the energy in joules if you multiply Planck's constant by the speed of light. If we were to take angular frequency, use that as wavelength, we'll probably get something like 2 pi in there emerging. See, now angular velocity is 1. Radius is now the speed of light. So this is how you explore the electromagnetic spectrum mathematically. Yep, see, look, here's momentum. Momentum has shifted to 2 pi now. We'll have to look at this a little bit more. So anyway, you always want to start out at 1 meter. 1 meter is your base point. That's where you get the speed of light for frequency. That's where you get Planck's constant. That's where you get this fundamental constant number right here for mass. The this one connects. This is the one that connects Planck's constant to energy, and the speed of light connects energy to Planck's constant, and this number right here. See, the speed of light and Planck's constant are connecting all these three numbers together over these three units of measurement. And this is how you mathematically represent them as they make their transition period from one of these units to the other. Like, these all take a shift. Like, if you take this number right here, which is 1 second divided by the speed of light, and then you use it as a wavelength. So what you're doing is you're essentially dividing this number by the speed of light again, and it gives you these numbers. See, this number is now here under momentum. Planck's constant has shifted to mass, and the one that was on mass is now force. So all these units shift one of these rows when you reach the speed of light squared in frequency. Okay, so there's my rundown on electromagnetic wave mechanics and how you should start at 1 meter for all your base measurements and all your, and that's where you get all your all your numbers for calibration to be able to explore the electromagnetic spectrum with.